So all we did was we just substituted back in for A. And then I'm guessing you guys can figure out what to do next with this. So if I was to ask you guys what to do next, what seems obvious?
Multiply.
Yeah, just multiply it out and it becomes quantity 4k, or just 4k squared. So 2b squared is equal to 4k squared by multiplication. Okay. And then, so what do you guys think we might be able to do?
Divide by 2.
Yeah, divide by 2 maybe. Sure. I mean, we could divide by 4, we could divide by 85 if we wanted to, but let's divide by 2. So we could say that b squared is equal to 2k squared by division. Okay. So let me give you guys to make sure that's all cool. Okay. And I haven't done anything, I don't think, too out of the ordinary at that point. Okay. So this is a little bit sneaky right here. Okay. So, any questions, guys, thus far? Mr. Rober? You're just making sure everything's cool? No question yet? Not yet, okay. All right. So, what can we say about b squared, if anything? That it's even, okay? So, thus b squared contains a factor of 2. Contains a factor of 2. And is even by definition of even. Okay, well that's nice. Well, if b squared is even, okay, what can we say then about b? It must be even as well. And how do we know that, guys?
Proof previously.
Yeah, it's right here. We proved it before. Okay, so we had it in. Okay, so thus, if b squared is even, b must also be even. And in parentheses, proved previously. I should actually say proved previously in this class, because for any of the proofs I give you, you could have said proved previously, but we don't know when they were proved previously, which is true, but it has to be proved in this class sometime. All right. So we got all this good stuff going on. Okay, so what? So we need to do a contradiction at some point, right, guys? I mean, that's the whole purpose that we're doing this. So have we arrived at any contradiction, or can we do any more substitution, or somebody give me something here so we can finish this off. So, Michelle? What's the common factor, Michelle? Yes, okay. Guys, the contradiction, okay, A must be even, right? So A equals 2K, okay? B must also be even, okay? Thus, B must be equal to 2P, where P is an integer by definition of even, right? Well, now what we see is that both B and A contain a common factor of 2 because they're both even. Okay, so thus A and B contain a factor of 2. Right. Now, why is it so bad that they contain a common factor of 2? Right, because didn't we say at the very beginning of the proof, we said that by the very definition of rationality, A and B must not share any common factors. So we finally come into a contradiction, okay? So that's the hard part of this, guys. The most difficult part of this proof, especially with contradiction, is sometimes you have to pull stuff out of nowhere to be able to derive your contradiction. And this is one of those types where you just have to go along with it and prove it out of nowhere. Okay? So, we could say that this is a contradiction. Since A comma B share no common factors. All right.
since A and comma B are supposed to share no common factors, but the proof shows that.
Right, this is a contradiction because A and B should share no common factors. Let's say that.
Why did we use P again when B equals 2P?
Oh, just because we wanted to show that it has the form of 2 times some sort of value, okay? Because remember, Andre, we're trying to show that it contains a factor of 2, or is even in this case, okay? So it's just 2 times some integer.
That part's the arbitrary part.
Right. We don't really need to know too much about that,
Okay.
okay? All right. Clearly, it's a contradiction, so that means the negation is false and the original statement is true, okay? So this is a contradiction, thus the negation is false and the original statement is true. Okay, so root 2 must be irrational. Right, bless you. No other way to prove it. Go ahead.
Okay, since we already have shown that A has a factor of 2, and in the initial we declared that A and B should not share. So if we just showed A contains a factor of 2, we don't have to do all this stuff.
We still do, because we have to show that B contains a factor of 2 as well.
But it's and. And means if one is false, the whole thing is false, right?
No, we definitely have to show that they both contain a factor of 2. We don't know that for certain.
If you don't
No, what am I
B
saying is,
has a
he's
factor,
like, it's that A and B share no common factors. So,
Right.
but if you use the terminology and, if one of the preposition is false, the whole outcome is false.
Right, but you don't know that B contains.
No, we already
a
know
common
that,
factor.
we already know A contains a factor of 2.
But we don't know that B does yet.
Right, yeah, until you prove that B contains the same factor as A, you don't know that they both have a common factor.
Right. Like right here, we don't know yet that it has the common factor, okay?
Uh-huh.
We know that they shouldn't share common factors. All we're doing is we're showing that they eventually
Oh,
have a
share.
Right,
Okay.
okay.
Share.
So they should not share a common factor by definition of rationality.
So share means like they should have like a same common factor or like.
They
say-
should, like for instance, okay, 3/6 is not rational because they both contain a factor of 3, right?
Uh-huh,
So when I say share, it means they both contain the same factor,
okay.
okay? Does that make a little more sense now,
Uh-huh,
Art?
gotcha.
We don't know that for sure up here because we don't know what A and B necessarily are yet, and that's what we have to prove and go through and do this. Okay, does that make sense now,
Yes,
sir?
it does, yeah.
Okay, good. All right. Yeah, it definitely is sneaky, okay? And as you guys go along, not in this course, but in other courses, the other proofs get even sneakier than this.
Especially since most math classes don't say that A and B share no common factors.
Right.
They just say simplify it.
Correct. All right, so that's why I'm trying to show you guys these sorts of things. And sometimes something even as I guess, maybe unassuming as that becomes like the major component in the proof. Okay, so, yeah, when you guys get to your higher level math classes, make sure you guys, when you're doing proofs, make sure you don't discount any of the given information. Okay, now, you guys know that we haven't used this yet, and I've said we're not going to use it until now. Okay. All right, for homework, I asked you guys to show that root 3 is irrational. And I give you guys the hint that if 3 divides a square, then 3 divides a. So you're basically going to do the exact same thing, except instead of using even, you're just going to use divisibility for that. Okay? So if you guys get stuck with it, come to me on Wednesday. I can try to help you in the right direction with that. All right. Questions about this proof, guys? Definitely a more difficult proof than what we're used to. Okay? Now, a little bit easier is the next proof that we're going to look at. So this guy's pretty easy. Oh, Adam, I'm sorry, and then Ryan.
So at the end, when you're saying this is a contradiction, because they should share no common factors,
Correct.
would it be okay to say this is a contradiction because A and B share common factors?
Correct, yeah, if you said like they share common factors because it contradicts this component that says they shouldn't, okay? So yeah, either way you want to do it, all you're doing is you're just pointing out that they have a common factor, okay? And we already showed it right there up top. We said that they both contain a factor of 2. So there's more than one way to write that ending. Is that how you're thinking of doing it? Which is perfectly fine.
I just
Sure.
want to make sure.
Oh yeah, sure, that's good, Adam. Okay, Brian, do you have a question?
Can I get a factor?
Oh yeah, sure, that'd be helpful too. Paul passed to Andre, Andre passed to Ryan. There you go. Okay. All right, guys, other questions before we go ahead and finish up with this one? Okay, so the next proof that we have is a lot easier than the previous, okay? This one says to prove that 7 minus 3 roots of 2 is irrational. Now, the good news is that we've already proved that root 2 is irrational, okay? So you probably already think to yourself, okay, it's going to be irrational, okay?
When we're doing something like the homework or on the exam, if there's a problem where we have to prove something like the square root of 2, can we use that in a following problem saying, oh,
And I would say
we already proved this previously in a different problem? Okay,
And what I would do is I would specifically spell out, you may use the fact that,
oh,
okay? So I'll do that. So now in real life, in another course, if you haven't proved it, you don't want to make that assumption, okay? So you don't want to say to your teacher, well, I already knew that. They're like, well, how do I know that you know it, sort of thing.
Okay.
So what you would actually have to do in another course, like if we were doing this proof and it was the first time we did it, we'd have to do a side proof, okay? So,
Right, right.
and
Well,
that
here's the
happens
first time,
unfortunately.
No,
Now, I
I'm
don't
just referring to using what we already have, or resources, I guess I
Right.
can call it.
In this class, I never make you guys do side proofs, okay? Once you prove something, it's one proof per problem, okay? All right, so here's our proof. Again, it contains a rational number. So, because it contains a rational, or irrational, we say suppose not. Of course, we're going to say suppose that 7 minus 3 roots of 2 is rational. So, suppose not. Suppose that 7 minus 3 roots of 2 is indeed rational. Well, if it's rational, what can we say about 7 minus 3 roots of 2?
Factor of A over B.
Yeah, equals A over B. Okay, so by definition of rational, seven minus 3 roots of 2 is equal to A divided by B. And just like before, A and B are elements of the integers, B is non-zero. Now, we don't need the fact that they should not share a common factor. Okay, so for this one, you don't have to write that. Okay? All right. So does anybody think they might know an approach that we could utilize, considering that we already just proved that the square root of 2 is irrational?
Since you're using the proof of the square root of 2 being irrational, you still don't need to mention that A and B.
Correct. We don't have to mention that they're
Because it's mentioned in that.
correct,
proof.
because we've already proved it in the previous. Okay? So we're just going to use that fact. So Don, did you have a
Can
suggestion?
you put like, can you change after the square root of 2 with another, like a letter?
Unfortunately, we can't say closure because it's not an integer value. Okay? So if it was just regular 2, then sure we could, but that square root just throws everything for a wrench. Good try. So any other suggestions, guys? So John?
We try to show that square root of 2 is equal to a rational number, like the kind of picture.
So maybe solve it for root of 2 first, and then that might get us somewhere. I like that, okay? So if you guys were going to solve this for root of 2, okay, do you guys have a suggestion as to maybe how you would start that?
Subtract 7.
Yeah, subtract 7 from both sides. No, John. So just by some basic algebra, we could say minus 3 roots of 2 is equal to A over B minus 7. Okay, so that's just by subtraction. We could get a common denominator and just meld this into a singular fraction, couldn't we, guys? So by common denominator, and like I said, I'll write the steps up in a moment, negative 3 roots of 2. If I was to write this as a single fraction with the denominator of b, what would the numerator look like, guys?
A minus 7B.
A minus 7b. The common denominator is b. A already contains a denominator of b. 7 needs the b. So a minus 7b divided by b. And then couldn't we divide both sides by negative 3, or multiply by negative 1/3, however you want to do it. So root 2 is equal to a minus 7b divided by minus 3b, right guys? Okay. And by the way guys, this is just all algebra stuff, okay? Nothing higher than algebra 2. So, but do those steps make sense, guys? Especially considering we've done rational stuff so far. And then, because of all this, what can we say that root 2 must be equal to eventually? Yeah, like m over n, p over q, s over c, whatever you want to call it, right? So root 2 equals m divided by n, where m and n are integers. Okay, now let's fill in the steps here. Okay, so before we do that, is everyone okay with the algebra to this, guys? Any questions? Okay. The first step, all we did was we just subtracted 7 from both sides, so that's just subtraction. The next step, we just got a common denominator. It's technically LCD / subtraction. Okay, that's easy. And then this step was division. And then the very last step that we did, that's just our friend closure. Okay, so let me go ahead and let you guys copy that down. So this one was much algebraically less taxing than the previous proof, or hopefully it was. All right, so my question to you guys now is, well, how is that a contradiction? Well, what is root 2 equal to?
You already proved root 2 is irrational and you're showing that it's rational.
That's a contradiction, right? Okay, and I think John outlined that very nicely at the beginning where he said, let's solve it for root 2, let's show that root 2 is rational, even though it's not rational. Okay, does that make sense to everybody, guys? I think it's a good approach when you're dealing with irrational numbers. Solve it for the irrational, and hopefully it equals a rational number. Okay? So here's how we can close this out. We can say, thus, root 2 is rational by definition of rational. As Mr. Weber just said, well, that can't be possible because we just spent 20 minutes